For a second experiment, we explored projectile motion by comparing two models, an experimental dataset obtained from real-world measurements and two theoretical models created using WebVPython. The main goal was to study how air resistance affects a projectile's motion and to estimate the drag coefficient. The key physics principles involved are projectile motion under constant acceleration and Newton's second law, which relates the net force of an object to its acceleration, and the drag force, which is represented as F drag equals minus b, which is a constant, times the speed squared times the direction of the speed, acting opposite the direction of the motion and depending on the square of the speed. So at the end of the experiment, we noted that the theoretical model diverges more from the experimental data when drag is ignored, showing that the importance of including drag to improve accuracy. For the experimental portion, we used a small paper ball with a mass of 5 grams. Its motion was tracked using an online video tracker which recorded horizontal and vertical positions at discrete time intervals. The system was calibrated using a known distance to ensure accurate scaling, with the x-axis representing horizontal distance and the y-axis vertical height. From the recorded positions, velocities were calculated as the change in position over time and accelerations as the change in velocity over time. So this provided a detailed representation of the projectile's real motion, which naturally included the effects of air resistance. For the theoretical model, we recreated the same motion in WebVPython. We first simulated the projectile without air resistance, where gravity was the only force acting downward. Using Newton's second law, the velocity and position were updated at each small time step, and the new velocity was the previous velocity plus gravitational acceleration times the time step, and the new position was the previous position plus the new velocity times the delta time, and this produced the parabolic trajectory expected for ideal projectile motion. Then we incorporated air resistance using the drag force. Drag was proportional to the square of the projectile speed and acted opposite to its motion. The net force became then the sum of the gravity and the drag, so using the same small time steps, velocity and position were updated with Newton's second law, and we noticed that including drag slowed the projectile, reduced its horizontal distance, and lowered the peak height, consistent with experimental observations. To determine B, we compared the experimental data with the theoretical model without drag, and the difference in trajectories allowed us to estimate the force of air resistance at each point. Applying Newton's second law in the horizontal direction, F drag was calculated as mass times the difference between the experimental and the theoretical horizontal accelerations. And knowing the drag formula, we solved for B as F drag divided by V squared. So instantaneous velocities from experimental data were used to calculate an average B, which was then applied in the theoretical model with drag to improve accuracy. Comparing the results, the no-drag model diverged from the experimental data over time, predicting the projectile would travel farther and land sooner. For example, at 0.7 seconds, the experimental exposition was about 2.3 meters left to the origin, while the no-drag model predicted 3.3 meters. In the vertical direction, the experimental maximum height was approximately 0.51 meters, while the no-drag model peaked at 0.39 meters. These discrepancies occurred because air resistance does both horizontal and vertical motion, including quadratic drag, and the simulation aligned the theoretical trajectory closely with the experimental results, confirming that air resistance significantly affects the motion of light objects. Before concluding, to answer the question, what does terminal velocity mean, and do any of the models predict it? Terminal velocity occurs when the downward gravitational force equals the upward drag force, resulting in zero net force and constant falling speed. In this experiment, neither model reached terminal velocity because the flight was too short and the projectile never fell long enough for drag to balance gravity. But terminal velocity could be measured by performing a longer vertical drop or using a wind tunnel. The projectile would fall until it stops accelerating and it reaches a steady speed. And this speed could then be used to calculate the drag coefficient B as m times g, mass times gravity, divided by the speed squared. For the second question, if the object were thrown straight up with the same initial speed, would the time to reach the ground be the same, longer, or shorter? Well, now if the paper ball were thrown straight up, it would stay in the air longer than in the angled launch, because in the angled launch, only part of the initial speed contributes to vertical motion, while in a straight up throw, the full speed acts vertically. And additionally, without drag, the time of flight is proportional to twice the vertical speed divided by gravity, so larger vertical component results in a longer flight. With air resistance, ascent slows and descent is delayed, but the total time would still generally be longer than in the original angled launch. In conclusion, the experiment demonstrated that including air resistance is essential for accurately predicting projectile motion. The drag coefficient B can be determined by comparing experimental motion to a no-drag model and solving for drag force. The results show that neglecting drag overestimates both range and peak height, while including drag produces a simulation that closely matches reality.